a mounting body of evidence has been growing that the structure of dark matter isn't what you would naively predict for a collisionless massive particle. So there's a number of problems that have been given colorful names. There's the too big to fail problem, which is an issue related to how many baryons, the smallest clumps of dark matter that we can observe, seem to collect and form into stars. You know, we can observe the kinematics of these stars, and we can see their motions, and we can get an estimate of what the amount of dark matter in this small halo sums up to. But there's, for the velocity profile of these stars, there simply aren't enough stars to explain how much dark matter there is. It should have collected more baryons and formed more stars. And yet, there are only a few hundred stars in these smallest dark matter halos, and that's a bit of a mystery. Then, on larger scales, you have the cusp versus core problem, where objects as large as galaxies or clusters of galaxies form hierarchically. And we know fairly well what the peak of the matter-power spectrum is from the WMAP experiment, and then later from the Planck experiment. But if you extrapolate those observations down to smaller scales, you infer that there should be a great many small dark matter halos, and that they should collect over time to form larger dark matter halos. And when you perform that summation, what you find is that you have dark matter density profiles which are very cuspy, very centrally concentrated, because you have a great many small halos that collect at the center of the larger halo and form a very dense knot. But what we find when we use gravitational lensing, when we look at rotation curves, is that these dark matter halos seem to flatten out. Either their cusp changes its equation of state, how its slope as it comes into the core, or into the center, or there is a smooth turnover to a flat core. And that is not phenomenology you expect from a collisionless particle. And lastly, there's the missing satellites problem. So when the dark matter is collecting into larger halos, as I said before, many small halos are gravitationally trapped and fall to the center. But as this process happens, there should be still many more halos that are in the process of infall into these large dark matter halos. So there should be many clumps of dark matter that are orbiting the large galaxy size and cluster size dark matter halos. And, well, we can go and count locally, right around the Milky Way. We're here, we can see stuff that's close to us. And there's about an order of magnitude fewer of these small clumps of dark matter than we predict. So, and just to draw a picture, here's what we observe for the Milky Way galaxy and our dark matter halo and our satellites. And then here is, roughly at the same scale, a computer simulation of collisionless dark matter. And you'll notice there's a heck of a lot more clumps of dark matter on the right-hand side than there are on the left. So, really the only way you can explain these missing satellites is that something is suppressing formation of these small clumps of dark matter. And so when you run the clock back to the early portion of the universe, really what you have to do is you have to stop small-scale structure from forming in the dark sector. So when a small lump of dark matter begins to gravitationally collapse, there has to be something there to provide pressure support, so that when the gravity squeezes on the lump of dark matter, pressure support pushes back and stops the small-scale structure from collapsing.
What is the statistical significance of this comparison?
This comparison,
so it could be that the numerical computations are actually wrong.
Well, it could be the numerical computations are actually wrong, but none of the current generation of numerical calculations have been able to identify any numerical problem with their calculation of the formation of this structure. And it's these halos in modern calculations are much larger than the smallest mesh size of the adaptive mesh grids. So it's no longer thought that this number of dark matter halos is a numerical artifact.
I guess what Francisco was actually asking.
What's the statistical error on the actual count of?
Exactly. Like
yes.
statistically, you might have like by chance, let's say. I mean, very few, just because it happened.
That's right. So this is so it may be that this problem is related to what I talked to you earlier about with the too big to fail problem, because if these small halos are not accumulating baryons, then they're not forming stars and we can't see them optically. So you can't spot these things with gravitational lensing, they're not massive enough. But
is that a statistical weight?
so the statistical weight at the moment is this, if you believe the error bars on the total number of Milky Way halos, satellites in the Milky Way halo, then the error bars are about 10 sigma. Now the question is whether or not there's some systematic error. That's just the statistical error. And there could be a significant systematic error there, but
this is a famous fact that we expect a supernova to explode every number of years, but then we don't see it.
well, no, that's actually if you're gonna quote the one supernova every 30 years number, everyone knows that that's the average rate, but you want to know what the standard deviation on that number is? It's plus or minus an order of magnitude. Right. Yes.
I understand though recently, and feel free to correct me, but recently they have been finding darker satellites, and also people are having things like baryonic feedback and other processes. I mean, I've heard recently that people are claiming that these are less of a problem than they originally thought, and there are various reasons why they think that it's.
So they have been so there are multiple problems with that claim. Primarily that when they say they find these darker satellites, there are so few stars in the smallest satellites that there's no good way to actually estimate the dark matter mass. The statistical error for the velocity dispersion that you measure, which you can only see the line of sight velocity dispersion. You can't get the proper velocity in total. You have to guess based on those line of sight velocity measurements. And with only a few dozen stars, the error bars on the dark matter halo mass that are associated with that particular halo are plus or minus a factor of 10. So they really don't know whether or not some of those smallest halos have large dark matter clumps associated with them or smaller ones. And even at that, there's still not nearly enough of those small clumps of stars to really explain this discrepancy, in my opinion.
So you think these problems are still...
Well, the dwarf spheroidals do not have enough baryons to have a significant supernova rate. In fact, you can measure the metallicity of the stars that they observe in these clusters, and there has been perhaps one supernova in the entire history of that cluster, and it's still devoid of baryons. And one supernova is not enough to clear out an entire cluster worth of cold gas. So baryon feedback really works best at the galaxy size, not so much at the dwarf scale, and not so much at the cluster scale, because when you collect clusters of galaxies together, the hot X-ray emission ionizes most of the molecular gas and shuts off the star formation in most large clusters, so that you have trouble forming supernovae to actually transport the baryons out of the cores of these clusters and then take the dark matter along with it. So baryon feedback really only works at the galaxy scale and doesn't translate very well to cluster scales or to dwarf scales. So back to where I was before I had this wonderful round of questions, because thank you, please ask questions, I love that. Back to where I was. In order to suppress the formation of these large-scale structures, you need to have some form of pressure support for the dark matter. So there's lots of material that we know of in the universe that isn't dark matter. There's baryons, but we've been looking for direct baryon dark matter interactions for a very long time now, and we know that the cross-sections there are so small that baryons can't be providing pressure support for dark matter. Even though the dark energy itself is somewhat mysterious, the pressure support that it provides has the wrong sign. You know, dark energy has negative pressure, so it's not actually going to stop a collapsing object from collapsing further, which really leaves us with the radiation energy density of the universe as the only candidate for providing pressure support for the dark matter. And luckily, yes?
The dark matter can't do it itself?
So the dark matter self-interaction, if it has a direct coupling, has to be too weak in order to do that itself, because we still observe that the dark matter collects into dwarf spheroidal scale structures at all. It wouldn't be able to do that if it had a strong self-interaction, strong enough to prevent this formation of structure early in the universe. So whatever was providing pressure support had to dilute away. So again, the candidate for that is radiation. And there's lots of it running around. There's about 10 to the 10 photons per baryon of the universe. But again, if dark matter has a electromagnetic handle, it has to be very weak. Again, you can say this from our direct observations of dark matter nucleon scattering. But neutrinos are hard to wrangle, they're hard to detect, and they're hard to make. And they're really the only candidate left for radiation that's left over from the Big Bang that might be interacting with dark matter. And it turns out that they're still very, very numerous even today. And if you go through the calculation and look at what the halo mass cutoff for suppressing dark matter structure formation with an interaction with a cloud of neutrinos in the early universe looks like, well, the mass cutoff goes like the temperature at which you get kinetic decoupling. So even though a neutrino will probably, an individual neutrino will probably never scatter with a single dark matter particle because there's 10 to the 10 of them per dark matter particle, one dark matter particle will scatter with many neutrinos over its lifetime in the early universe. So it will transfer a lot of momentum. So the temperature at which that process cuts out sets the mass scale at which you can push on a lump of dark matter and get pressure support back. And when you compute what that kinetic coupling is, you find that for a neutrino coupling at the Lagrangian level and a mediator mass that governs the interaction between this neutrino and dark matter, a coupling that is roughly, in order to get a cutoff mass which we need to explain the missing satellites problem, a coupling that's roughly 10 to the 8 times as strong as the weak interaction. So this is something close to a nucleon scattering cross-section. So 10 to the minus 30 centimeters squared for a dark matter neutrino interaction. And that's very, very large, but again, this is neutrinos directly interacting with dark matter, so this is not necessarily the neutrino cross-section that we observe for the weak sector. So to draw a Fireman diagram of our first little puzzle piece, this is what that looks like. We have the dark matter particle propagating along, and it exchanges, I've drawn a vector boson here, but it doesn't necessarily have to be a vector, and forward scatters off of a neutrino and transfers a little momentum. So another dark matter structure problem might be solved with dark matter interacting with itself, a pair of them. So the cusp versus core and too big to fail problems might be related. And these two pictures are from a very excellent paper by a collaboration between Caltech and UC Santa Barbara, where the scientists went and looked at a collection of galaxy clusters and used weak lensing and measurements of the stellar velocities in these and the galactic velocities in these clusters to probe what their what the dark matter density profile looked like over 3 orders of magnitude in radius. And what they found was that when they fit the outer radial profile of these dark matter halos, that the inner radial profiles did not match up. So you have the isothermal Navarro-Frank-White. Essentially, beta is the parameterization of the slope as the dark matter profile comes into 0 radius.
So this is assuming NFW, and then
so
you're
that vertical line
beta in NFW.
that would be beta in NFW. And then here is the fit to the observations of lensing and velocity dispersion in the galaxies that show you where the best fit lies. And so many of these galaxy clusters seem to have, if not a core, at least a change in the slope that is not consistent with the isothermal profile. And
sorry, this should be all coinciding in the same point.
So not all of the clusters necessarily have the same mass and same kinematic history, so they don't necessarily have the same inner slope.
So in other words, what are the different colors here?
Different colors are different clusters. So not all. So some of the
Different types of
clusters.
clusters, or what? Sorry, or literally just different.
Yeah, different clusters. Different clusters.
So when you say compared to NF,
The dotted line is the fit to the NFW profile in the outer portion of the halo. How well does that match the slope in the inner portion of the halo? And all of these clusters seem to disagree about what the slope of the isothermal profile in the inner portion is relative to the outer portion. And here's another example. Here's a calculation where they made a statistical estimate of how core the inner profile was. So some of these, a few of the halos have a statistically significant core. Some of them simply, woo, why did that, hello. All right, went to sleep. Some of these halos don't have a core, but they still seem to change the slope of their inner profile. So, in order to use self-interacting dark matter to explain this, you have to be a little bit crafty because the observations don't support a single dark matter interaction cross-section that is independent of the size of the halo. The mass of the halo from the observations seems to decrease the amount of self-interaction between the dark matter that you need in order to explain the distribution of mass with radius. So for instance, here we have the bullet cluster that's very famous. Now you can see the X-ray emitting hot gas that's been shocked by the collision of these two clusters. But then in blue you have the mass distribution that's inferred from lensing. So you can see that the dark matter has more or less passed through itself when the center of mass velocity difference is about 1,000 kilometers a second. But yet the matter has definitely self-interacted and formed a nice bow shock that lets you actually measure what that center of mass velocity was. In order to use self-interaction to explain why you can have phenomenology like this and what I showed you in the last slide, but also have dwarf galaxies that don't accumulate enough baryons because they have washed out cores, you need a momentum-dependent interaction. So you need some kind of Yukawa coupling that allows momentum dependence to shift to low velocity. So larger cross-sections for lower velocity interactions, smaller cross-sections for high velocity interactions. And recently, last year, Tillinyu and Zurich showed that you could use this mechanism to reconcile all of the observational data about clusters, galaxies, and dwarfs into a single unified picture where, for attractive dark matter self-interaction and repulsive dark matter self-interaction, there are bands depending on the properties of the mass of the mediator particle that allows dark matter to talk to itself and the strength of the force that fit all of the observations, basically in the classical, the quantum scattering, as they call it, and then the Born approximation regime. So it's very possible for one new mediator particle to allow dark matter to talk to itself and explain the lack of cusps in the center of the halos and the lack of baryons accumulated by dwarf galaxies. And in a separate context, it's actually possible to use that same mediator to then be the mediator which governs the interaction between neutrinos and dark matter. So you can have a choice of, this paper did a calculation that was performed in the Born approximation limit. So this piece of these graphs, where the authors showed essentially that you can have a coupling to neutrinos that is strong enough to suppress the formation of small-scale structure with that same mediator. So that the new mediator particle that talks to neutrinos and allows dark matter to talk to itself can have a unified picture that explains all three of the problems with the structure of dark matter that exists today. And
when you say couple to the neutrinos,
yes,
you're going to show the interaction.
Oh yes, don't worry. You have to wait a little bit, but I will get there. All right. So, and also if you relax a few of the assumptions in this paper, there's a much broader parameter space actually that allows for all three of these structure formation problems to be solved simultaneously. So, there's still a few missing pieces here in terms of this neutrino portal because you need, if you just look at these, there's obviously a Feynman diagram that you can draw here that I haven't drawn yet, and it's this one. So if you have a vertex that couples two neutrinos through a new interaction, it can absolutely couple neutrinos to themselves. And this becomes a very interesting prospect. So we've been talking about cosmology now and the structure of dark matter. And if we want to now think about what might be going on with neutrinos self-interacting, we should probably go to a neutrino telescope, because that will actually let us see how neutrinos are behaving over cosmological distances. So enter one of my favorite experiments, the IceCube detector, down at the South Pole. And this is a very, very large detector. So there's about 3 kilometers of extremely clear ice under the South Pole. And very smart people had the very bright idea of using that as a neutrino detector, as a water Cherenkov neutrino detector. And what they did was they used hot water to drill and lowered strings of photodetectors down into the ice and instrumented it to look for the flashes of Cherenkov radiation that occur when high-energy neutrinos that have propagated from cosmological distances arrive here at Earth and happen to bump into a proton. You know, they traveled a gigaparsec, but here was where they decided to find a proton and be happily ever after. But, you know, there's something, you know, funny about this. This is a cubic kilometer of ice that we've now instrumented. And as an interactive question, why do you think they made it so large? Why did they make it so big? They're not just greedy. So the easy answer is that they're greedy experimentalists and they want as much fiducial volume as they can get their dirty little hands on. That's only part of the answer. The other part of the answer is what you want to be able to do is contain all of the energy of the events that you're trying to reconstruct. And neutrinos, which propagate from very, very far away, typically will have very, very high energies because they come from the most violent events that occur in the history of the formation of our universe. So they're going to be depositing a tremendous amount of energy, 10 to the 6, 10 to the 9 GeVs of energy. And you need to have a detector large enough to actually contain the light flash that lets you construct that event. Yes?
Why don't they build an Eiffel Tower at the bottom of the
For scale. For scale. You know, what the joke on Reddit is that, you know, you put a banana in for scale, but that's sub-pixel size on this. So this is the gentleman's banana for the IceCube experiment. All right. So high energy neutrinos. Well, as I said, the formation of our universe was extremely violent. Black holes, AGNs, exploding stars. And this is actually one of my favorite galaxies that we've observed so far. This is a galaxy called the Cartwheel Galaxy. And what happened here was an ordinary spiral galaxy a few 100 million years ago had a collision with a smaller spheroidal galaxy face on through the disk at high velocity. And what that did was it set up a pressure shock wave in the cold gas of the galaxy that propagated outward through the disk. And when the shock wave passed through the cold gas, it triggered a rapid star-forming epoch. And so this bright blue ring around the edge of this galaxy is actually behind the pressure shock wave. And these are all of the bright blue supermassive stars that were formed by the passage of that shock wave. And behind this bright blue ring of stars is another ring of supernova remnants, because supermassive stars only live for a few million years. And so this collision of dark matter clumps actually set off a chain reaction of supernova that produced all sorts of high-energy neutrinos. And why do you get high-energy neutrinos out of violent events? Well, ultimately, it comes from protons. Anytime you accelerate, protons to relativistic velocities, eventually it's going to bump into something because the electromagnetic interaction is strong. And when you knock things into protons at very high energy, you almost always get pions out. You know, they're foregrounds in modern particle colliders, but they're most of what comes out of proton collisions. And when you make pions, you have about a 50-50 chance of making neutrinos. You make a pi naught, it goes right into photons. But when you make a charged pion, either a pi plus or pi minus, you make 3 neutrinos as end products of that collision. So primary candidates for producing high-energy protons as a consequence of high-energy neutrinos, gamma ray bursts. So supermassive star collapses, forms an accretion disk in the center as the envelope is being ejected after the collapse, and the jet, with strong magnetic fields, accelerates protons up to very, very high energies of 10 PeV or so. And those protons then collide with the expanding ejecta and produce pions that decay to neutrinos, and those neutrinos are what we want to collect with the IceCube experiment. And so this process looks like this. And if you sum over what we think the supernova rate and the GRB rate for the history of the universe is, and look at what the incident flux we expect to get at Earth is, you wind up with a number. You know, here's a prediction for the GRBs. But if you just assume that the efficiency of all the protons that we observe from cosmic rays being turned into pions that produce neutrinos is maximized, so 50% of all the pions ever made in the history of highly accelerated protons end with neutrinos, you wind up with a neutrino flux that lands in this kind of cosmic ray limit region right here. So IceCube is now probing this level of flux. And in addition to GRBs, you can also have simple jet emission from things like active galactic nuclei. And so AGN jets are able to accelerate protons to even higher energies because their length scales are much, much larger than the GRB length scales. So a GRB has a core that is probably a black hole that is about 1.44 solar masses. And the acceleration length scale for those protons is only a few tens of kilometers to 100 kilometers. Whereas AGNs are the supermassive black holes at the center of galaxies, and they have whole parsecs over which to accelerate protons. So you can get protons to a factor of 10 to the 9 GeV in energy before they start to run into CMB photons and things and create photopions. And those neutrinos still come out, and they still arrive here at Earth, and we can hope to measure them. But what energy ranges are interesting for us? So, the largest cross-section that you're going to get out of you having some massive mediator allow neutrinos to talk to one another is a resonant cross-section. Neutrino antineutrino makes a mediator on shell that then decays. So that happens when the center of mass energy is the center of mass energy of the system. So a high-energy neutrino propagating over cosmological distances, most of the neutrinos that it meets along the way are going to be relic neutrinos left over from the Big Bang. There's 336 of them per cubic centimeter, and there are gigaparsecs to travel. That's a lot of neutrinos in between the source and yourself. So if you work out, this has been thought of before in the context of the Z-burst, because we know standard model physics. You can have a resonant production of a Z boson, but the high-energy neutrino that you need to do this, that center of mass energy has to be a few hundred GeV. That means that the energy of this the energy of the cosmogenic neutrino has to be 10 to the 13, 12-ish GeV. So that's much higher than we expect for these AGN and GRB neutrinos. But if you just go back and put in our new mediator that we think might be related to the dark matter structure problems, we can get an estimate of what its mass ought to be, just because PeV neutrinos are what's being produced in these GRB events and AGNs. And the neutrino mass scale is something in the neighborhood of 50 millielectron volts. There's at least one mass eigenstate that's somewhere in that ballpark. And that gives you a center of mass energy of about 10 MeV. That is a very, very interesting number. Because, and you can't, this isn't blurry on the screen, my apologies. But if you go back to the mass scales for this dark sector mediator that allows you to solve the dark structure problems, 10 MeV right here lies right in the middle of the parameter space that you would like your dark sector mediator to lie in order to solve dark matter structure. So does IceCube see anything interesting? It's been running for 3 years now, and they have a statistically significant result. They've found the flux that comes from GRBs and AGNs. It's 5.5 sigma above background now after 988 days of observing. And here's an example of their events from their latest paper that went on the archive just a few weeks ago. And the nice thing about this is that the distribution on the sky is not consistent with local sources. It's isotropic. It's coming from the whole sky, and it's not, the black hole at the center of our galaxy is pointed at us somehow and producing these neutrinos. That has been ruled out. So in terms of how saturated the signal is, well, the IceCube signal lies right there, right at the upper limit of, predicted by Waxman and Bacall 15 years ago. There are about as many neutrinos as you can possibly produce, accelerating protons in the early universe. So is this IceCube signal weird? Yeah, it is. It's delightfully weird. So if you take the best fit flux that fits their spectrum, there's kind of two chunks of the signal space where events are missing. And the fun story about IceCube is that they were originally looking in this empty box looking for events because the AGN flux is predicted originally to be much stronger than the GRB flux. So it's higher in energy, and they expected most of their signal to come from this window. But it didn't. They found these two, Bert and Ernie. And when they changed the energy of the box where they were looking for events, they found a number more. But there's still a couple windows of events that are missing. One between about 300 TeV and 1 PeV. And then the entire AGN portion of the signal above 3 PeV is missing. There are no events there.
So the blue and yellow are not real even?
They're not real. They are, so the black is the real data that I showed earlier. Right? This is the actual observed events. But if you take their best fit to the flux, this is what they should have seen. And so the absence of events is now at about 3.5 sigma in terms of its statistical significance, if you just take their best fit flux.
So by best fit, you mean you calibrate to the low energy, low.
You calibrate to the continuum.
Those
Yeah, you fit the whole signal.
But if AGNs are supposed to, but how does that work? Because you're also saying that AGNs is what is supposed to give you.
Don't spoil one of my big points later. No, you're absolutely right, Mass. AGNs are supposed to give you a great deal more flux. So that's.
Sorry.
But if AGNs don't.
But how do you fit? There's so much,
This scatter is just the inclination angle.
Right.
If you fit as a function of energy, I don't, unfortunately, I have those.
Sorry, maybe what's the difference between the X and the dots?
So IceCube can classify two distinct types of neutrino events. So when a muon neutrino enters the detector and undergoes a charged current capture, it produces a muon that then leaves a track of Cherenkov radiation through the detector. And so that's great for pointing and identifying the source of the muon neutrino. But unfortunately, when you have either a tau or an electron neutrino captured via the charge current, the tau decays too quickly and the electron loses energy too quickly from frequent scatterings because it doesn't have enough mass. So you get a big flash that's omnidirectional. And that is the same kind of signal that you get from a neutral current scattering. So a neutrino comes in, exchanges a Z boson, and that just creates a flash of light because you have either an electron or a neutron, a nucleon recoil, and scatter around makes a big flash. So there's two kinds of events, showers and tracks. But they can still get an estimate of the directionality from the timing of the light distribution in the big flashes. So it's not as good as a track, but they can still get pointing.
So it is clear that there are holes, right? Because the blue and yellow are not there.
Yes.
That is clear to me. How well is the fit?
So the fit is very interesting. So their fit, if you just integrate it across the entire spectrum, is if you take that as your prior, then you have a fit that is in 2 sigma of tension with the best fit. So the best fit that they have for a flat spectrum, 2 standard deviations of tension. Which is it's not great. Like, you'd like your best fit to be better than that, but it's not conclusive by itself until you see what they were originally predicting. So let me get to that. So these holes in the signal. Well, at this point, 2 sigma, it could be low number statistics, right? Those holes could just be statistical fluctuations. One hole is missing about 3 or 4 events, another hole is missing about 5. Maybe it's just a fluctuation. Another explanation is that there could be, sampling bias. IceCube uses a very sophisticated neural network that no one else understands, so it's easy to criticize to reconstruct their events. So the data analysis might be strange. But there might be, new quark physics that we are actually uncovering with this neutrino signal. Some people have postulated that. But really, the number one effect that people appeal to is that the source emission may not be understood. And some people beg to differ. So there's kind of a canonical paper that was the canonical paper for a very long time, about 14 years, on model-independent estimate of the emission of high-energy neutrinos from AGNs. Now, when you use model-independent in the title of your paper,
it's never independent.
There's always a model.
Yes, there's always a model. There's always a model. But for about 14 years, this was the industry gold standard for what they expected. This is the paper that built IceCube. And you can see why here. So this is the best fit prediction of events. But if you take the AGN flux from that paper and make a prediction for what the events that IceCube should have seen, it should have looked like this. There should have been 45 events with 3 years of data. Yeah, in this high energy window. And now the missing events at high energy is much more statistically significant. The fit to the actual data set is now terrible. So what explains this absence of events in IceCube? You know, well, here's a little cartoon that I drew, and IceCube is sitting here to scale. I told you it was big. And we have an AGN out in space, and it's emitting its high energy neutrino. And, oh, don't fall asleep. There it is. And then we have a nice little cartoon character pop up and steal our neutrino on the way to the detector. And that's not really what I mean. And, you know, this, as I told you before, the Z-burst has been well studied. People have looked at high energy neutrinos making Z's on resonance for a very long year. You know, started with Tom Weiler, and people keep coming back to this idea. And in order to have our interaction, here it is, I've finally written Lagrangian down for you, for neutrinos to talk to themselves, we've coupled them through a massive vector boson, and they specifically couple to a new sterile neutrino state, and I'll explain why in a moment. But you have your basic tree-level scattering diagrams, S-channel, T-channel.
Sorry.
Yes?
These are direct neutrinos.
These are direct neutrinos, that's correct. And you have neutrino.
Going beyond the standard model.
We are, well, if you want to be strict, massive neutrinos at all are beyond the standard model. Standard model, in strict interpretation, does not have neutrino oscillations. Yes, this is beyond standard.
There's no need necessarily to have that.
Yes.
To understand the minimality of the approach.
Yes.
I mean, I can just copy the Z and make something like the Z and only have neutrino of the standard model.
Yeah, but they don't mix. They don't mix. But we observe mixing in nature.
No, but you mean also the mediator, using Z as the mediator.
Oh,
but that's the problem with the center of mass.
But that's, yeah.
Another Z. I mean, all I'm saying, I could have written as a new diagram, a new 1 mass gamma 5 as the 2 new.
Yeah, but it wouldn't. But that other Z would not interact as a weak interaction eigenket. You would not be able to have a interaction between the weak sector and whatever that new particle was.
But you're only interested in coupling this to that matter.
That's right. That's right.
Can this interaction actually affect the oscillation, the neutrino oscillation?
The neutrino oscillation. It can, yes. And there's hints. I mean, I'm not the first person to think that there might be sterile neutrinos. Sterile neutrino oscillations have been.
This is not the neutrinos on the model. They are. I'm trying to understand.
Okay.
Are these neutrinos on the model or not?
So you can have. So this is an interaction that you can get out of a seesaw mechanism, where in.
Okay. And you has the standard model.
No, sterile.
It's sterile.
Something else.
Yeah, it's sterile.
That's fine. I'm trying to understand.
Oh, well, so if you want the description of what this is, when you have a seesaw mechanism that generates neutrino mass in the standard model, you can associate the gauge boson that comes out of that symmetry breaking either with the active neutrinos or with the sterile neutrinos.
These are the sterile.
And so we've chosen to put that gauge boson in the sterile sector. Yes. And you can have a 2 to 4 interaction between neutrinos that produce multiple mediators that then decay into
so this
other
in
neutrinos.
principle not the one that, for example, the active nuclei might actually do, because if they've been created with the standard model, there might be...
No, none of the sources create sterile neutrinos. None of them create sterile neutrinos. They make active neutrinos exclusively. Yes.
So you need to go through, in order to actually add this physics to the next step.
Yeah, there has to be some mixing. That's correct. So we can just write down formally what all of these cross sections are, where gamma now here's the width of our new interaction. And for the younger members of our audience, here's a refresher on what all the model sum variables are. And we can write down what our cross sections are. And sure enough, if you pick the correct scalings for this coupling constant, you can get a nice large resonant cross section that will produce absorption features. But we have to be careful, because as I was just discussing, I'm sorry, what's your name? Francesco. Yeah, as I was just discussing with Francesco, you have to have a sterile neutrino, and you have to couple it to the active neutrinos through mixing. And that's because LEP and rare kaon decays very strongly constrain what the Z boson width is and what the branching ratio in decays to invisible non-leptonic sector processes could be for neutrinos. So you have to have this definition that this sterile state, whatever it is, it cannot be a weak interaction eigenket. It has to be orthonormal to it. So once you make that definition, then this new coupling constant is more like, in the small angle approximation, the mixing angle times the actual Lagrangian level coupling constant. So now we don't have...
How heavy are these neutrinos also?
What's that?
Your sterile neutrinos, how heavy they are?
How
heavy?
Heavy. So they can be anything less than about a keV. So if they're more massive than a keV, there are problems with the early universe, but if they're less than a keV in mass. So they're not the dark matter themselves. Although there's kind of an interesting window on the far side of that once you get above 4 GeV, where the steriles could be extremely massive again.
So there are no constraints from CMB because, I mean, you have like extra relativity because of...
There are constraints from the CMB, and that's a little further down in my talk, so I'll address that point. So we don't have the Grinch actually stealing our neutrinos anymore. What we really have is the cosmic neutrino background contains background neutrinos, either one of the active neutrino mass eigenstates or this new sterile mass eigenstate. And we have our neutrino from our AGN comes along. And because this is not a weak interaction eigenstate that allows this vertex, it counts as a quantum measurement of the interaction basis of this high energy neutrino. So if a neutrino goes through this interaction, it's taken out of a weak flavor state. It no longer talks to nucleons and electrons. So after it's done scattering, all of the decay products are in the sterile interaction eigenket. So these high energy neutrinos, if they have one of these interactions, will now no longer interact with IceCube when they pass through the detector. Now, yes? Yeah, that's the mass eigenstate of the sterile neutrino. Number 4 is the sterile neutrino mass eigenstate.
1, 2, 3 would be standard model.
Those, yeah, 1, 2, 3 are the standard model. Yes.
Sorry, so only when it is before you IceCube won't see it, otherwise you actually see it.
That's exactly right. Yes. So, yeah? Do you have a question, Mass?
Oh, sorry, I mean, in principle, both in the initial state can be standard model, right? And you still can go to 2 sterile.
Absolutely. The amplitude is down by another factor of the mixing angle squared.
So the dominant one
This neutrino doesn't need to all depends on the game.
Well, okay. Yeah. Yeah. So, that was a very smart question about what's left over from the Big Bang. So we need to actually compute what the relic density of that mass state 4 is, because that will have a much larger amplitude to absorb high energy neutrinos, because it doesn't need to oscillate into the sterile sector in order to scatter with these high energy neutrinos. So we have this self-interaction Feynman diagram, and then we have this weird, funny bubble diagram. And you'd think that this thing, nobody would care about this thing. You know, it's computed for QCD, and they computed it for active neutrino oscillations about 30 years ago. You'd think it wouldn't matter that a sterile neutrino could propagate and have this bubble diagram appear at finite temperature and then just keep propagating. But it turns out that this is an extremely important contribution to the effective mass. So in the early universe, this interaction may be thermally populating these sterile states, but then there's a second order correction of the effective mass that might shut down this interaction here on the left-hand side. And the reason for that is neutrino mixing itself. Just a simple example of a two-flavor system. The effective mass squared, right, so this is the oscillation frequency squared of 2 neutrino eigenstates, 2 neutrinos oscillating in flavor, has a term that goes like, the diagonal portion of the mass squared difference, and then the off-diagonal portion. But then there's this A factor that shows up, and that is the effective mass term that enters into the mass squared splitting between the neutrino mass eigenstates. So the further apart the mass eigenstates are, the lower the mixing angle is relative to its vacuum value. So you can have a vacuum mixing angle that might be 0.1, 0.01, but if you have a large effective mass, suddenly this becomes suppressed dramatically, proportional to the size of the mass difference between the two states. So you might have in vacuum, a 1/10 of a radian mixing angle, but at finite temperature, your mixing angle might be 10 to the minus 7 radians. And you can go about the dirty, dirty business of actually computing the effective mass contribution, and you just have to do this miserable central value integral, and at finite temperature. And so here, these gamma terms are simply the four-dimensional delta function of the Fermi-Dirac distribution of neutrinos and bosons that are involved in this bubble diagram. And so here we have the propagator for a neutrino, and here we have the propagator for our boson that's running in this loop.
So for doing these things, you're assuming that this sterile neutrino are in a thermal equilibrium, otherwise the plasma mass will not actually make any sense.
That's
So
right.
What thermalizes it, given it doesn't have any standard model pattern?
Well, so there is an amplitude, right, a calculable amplitude for the active neutrinos to go through that vertex. And so what we find, and this is just an example of what happens if you have a thermal distribution, but you just suppress the number density. So it has this thermal shape, but not the total number density of the thermal distribution, to this potential. And the figure of merit here is that for delta m squared over 2e must be smaller than this potential in order to have mixing angle suppression. So for the early universe, the energy of the neutrinos is about like the temperature, and delta m squared, just as an example, we'll take 1 electron volt squared, because that's about the mini-boon sterile neutrino signal. And that gives you that the delta m squared over 2e value is about 10 to the minus 6. And if you have very, very small populations of sterile neutrinos, you find that this bubble diagram very much suppresses the mixing angle between the active sector and the sterile sector in the early universe. You only need a tiny amount of the sterile population in order for that bubble diagram to shut off the mixing and shut down the thermal population just through that S-channel diagram and the T-channel cross-sections to produce sterile neutrinos in the early universe. So, and that size, that mixing angle is critical. We have our two main interactions that produce sterols here, but the number changing between active and sterile interactions, you put flavor labels on these things, it either goes like, theta squared, theta to the fourth, theta to the sixth. So if theta is a very small number, even though this interaction might be 10 to the 8 times as strong as a weak interaction, these things can very easily be much smaller than 10 to the minus 4, 10 to the minus 2. So raising the mixing angle of these high powers suppresses that cross-section. And suddenly, even though you have very strong Lagrangian level coupling, you have very slow interaction rates in the early universe because this mixing angle is so very suppressed. So you can actually solve the Boltzmann equation under these conditions, and this is what we find. That, indeed, if you start with absolutely no sterile neutrinos at all in the universe, so the symmetry breaking that produced the neutrino mass difference happened at some very, very high temperature, right? And there's no relic sterile neutrinos to begin with at all. You can push it to lower temperature and make lots of them if the decoupling happens at low temperature. But in the opposite limit, we find that the sterile neutrino mixing angle very, very strongly suppresses the formation of sterile neutrino number density. So at temperatures of a few hundred MeV, 10 to the minus 8 sterile neutrinos per active neutrino exist in the universe. And at a temperature of about 15 MeV, the active neutrinos actually freeze out of the plasma from the Big Bang. The weak Bremsstrahlung processes are no longer faster than the Hubble expansion rate, and you wind up with a fixed amount of entropy density in the sterile neutrino sector. So now at this point, the total entropy density of the active neutrinos and the sterile neutrinos is fixed. And as the temperature cools down, you go through resonance with this bubble potential. You start making it on resonance. And that process greatly increases the number density of sterols, but it's very, very narrow and doesn't actually fully thermally populate those sterols. But as you move on, it turns out that that T-channel cross-section, because it counts as a quantum measurement of the interaction eigenket of those neutrinos, thermalizes the neutrinos at later times, below an MeV. So now you haven't produced any additional delta N effective. Delta N effective is about 2 times 10 to the minus 7 times the total number of sterile species. But you've converted, because of this T-channel equilibrium that achieves later, when the mixing angle suppression goes away at low temperature, a significant number density of sterols. So now you have about a quarter of the relic neutrinos left over from the Big Bang are sterols, a quarter to a half. So we can scatter on this background of relic neutrinos. The temperature, because you have 2-to-2 processes, the temperature of the sterols and the temperature of the actives is the same temperature. And it's the same temperature that you get from ordinary Big Bang nucleosynthesis. The temperature of neutrinos is about 4/11 to the 1/3 times the photon temperature. And because of Liouville's theorem, it actually retains its relativistic fermion distribution for the rest of the history of the universe, because the neutrinos decouple from themselves and they can't change their phase space occupancy. So even though they might be non-relativistic at later epochs, they still have a distribution which retains that shape. And when we compute these cross-sections, we have to take that into account in order to convolve the thermal motion of the C B with the cross-section to scatter through the S and the T channels. And so that's what produces this thermal broadening. So if you have non-relativistic neutrinos, it makes nice, sharp, resonant features. But as the neutrinos become more relativistic, the intersection angle narrows the phase space down and smears it out across energies. So that what you get from this convolution is that the resonant absorption is broadened out. And so now it can get a very large window of energy space.
Even though they are not relativistic, but they have the relativistic.
No, these guys are relativistic.
Those are truly relativistic.
These are truly relativistic.
But you have the same effect even if.
This is non-relativistic, but it's not as pronounced, right? You can see that it's lowered the peak about an order of magnitude, and it's more visibly broad. But the interesting thing about this thermal broadening is the total optical depth across resonance is the same. It's conserved across all of these cross sections. It doesn't matter what the temperature is, but the temperature simply how relativistic the neutrinos are. But that simply affects what the energy range that the resonance covers. So a single neutrino will see the same optical depth from that cross-section, and that cross-section. And we can compute that optical depth. We take source spectrums for GRBs and AGNs and evolve the universe in redshift as using the best fit from Planck. And we can then compute the number density of relic neutrinos, their temperature, their energies, and the proper distance along a neutrino world line, and get an optical depth for absorption. So here's our probability to absorb in a redshift interval dz. And we find that there's a different functional dependence on the Lagrangian coupling for continuum absorption and resonant absorption. So this optical depth for resonant absorption that makes those peaks only depends on the coupling constant squared, and that's because that affects the width of the resonance. Right? The cross-section itself is independent of that coupling constant on resonance, but the width of the resonance is very narrow, and so the coupling constant comes back in. However, for T-channel absorption, you find that there's now 4 powers of that coupling constant which enter into the expression for the optical depth. But T-channel absorption isn't functioning at only a single resonant energy, so you have the entire multiple gigaparsec long world line of neutrino travel to absorb through this smaller cross-section that you might have. And so here I plotted orange with hatches and orange with solid. Hatches are the sterile neutrinos, solid or the active neutrino. So to have a background sterile neutrino would do the absorption versus a background active neutrino do the absorption. And orange is resonant absorption regime. Black, down here in the corner, is continuum absorption only. And then purple is a combination of the two at the same time. So you can see you can either have a flat continuum absorption, you can have a combination of continuum absorption peaks, or you can just have peaks. And when you look at the final flux, this is what it looks like. So we have in black dashed line here the original emission spectrum from the sources as it arrives at Earth. The blue dashed dotted line is the background for the IceCube experiment. These are atmospheric neutrinos. And then the color scale for resonant absorption, continuum absorption, the combination of the two, is plotted here, same color scale from the last slide. So the neutrino events that are observed in IceCube exist here and here. So this is kind of one of our favorite fits for the IceCube signal, where the first, the heaviest active neutrino mass eigenstate is doing the absorption in that patch of events that I colored blue earlier. And then the lightest neutrino is relativistic at the current epoch, and it's wiping out the AGN signal entirely. It's just absorbing all of the high-energy neutrinos because it's been thermally brought up.
Yeah, MEV.
MEV, you mean MEV, right?
Excuse me.
Not
Oh,
MEV,
my
because
apologies.
otherwise you wouldn't have
Yes,
much,
that is a
use
typo.
for this
People at
one.
home, that's a
Sorry.
typo.
Yes.
Yes, this should be an M, and then an M there. Yes, thank you.
Let me understand again.
Yes.
Which are the actual curves we should be looking at, and the yellow and the blue? Which are the actual curves where the...
So the orange curve is resonant absorption. The purple curve is resonant absorption and continuum absorption function at the same time. And then the black curve is continuum absorption only, what you expect for the final flux. And this is our favorite model, but it's not the only one that works. So in this case, you can have more massive mediators, which are still allowed for resolving dark matter structure. And you could, for instance, only wipe out the AGN signal. So it may be that some of this...
Why do I have this kind of oscillatory...
So these resonances come from when the neutrino energy, center of mass with the absolute mass eigenstate of the relic neutrino are on resonance to produce an effect. And it has a shape that isn't just a perfect spike downward because there's a redshift history behind the sources. So the source distribution as a function of redshift changes. So
three resonances.
Yeah. So it digs out a trough. And unlike Z-burst physics, where you have very, very distant sources that are so far away that these troughs run together, AGNs and GRBs are typically concentrated around a redshift of 2. So the troughs are distinct, and you can actually see them separately. So how well does this fit the IceCube data? Well, it kind of fits fantastically well. So here we have the blue line is that background that I talked about before. And then here's the green line is the IceCube best fit. But you'll notice that, in the AGN sector, summing all over all of those bins, it's about 1 more event. There's about 2 missing events for the Glasgow resonance. And there's 3.5 to 4 events missing here in that blue region where it seems to be a gap between 300 TeV and PeV. But when you have these absorption features, suddenly you get an absorption feature. The orange line is the 10 MeV mediator absorbing neutrinos here on the heaviest mass eigenstate, here on the middle mass eigenstate, and then here AGN on the lightest mass eigenstate. And it wipes out all of the high-energy neutrino emission, except for a little teeny window here that you observe in IceCube. So this is
tuned by choosing the mass.
Which is so you tune the location of these peaks by choosing the absolute neutrino mass scale and the mediator mass. And
so could I just ask one thing?
Yes.
On the previous plot, if I took GRBs away, how would the AGN, just the AGN look? Where would it start? What?
Down there. So this signal here, this is definitely GRBs. If you extrapolate.
But the AGNs, where would the AGNs start?
Start would be down here. They'd be buried by the noise. You would see, for the low energy portion of the IceCube signal, you would see background. So this comes down linearly. So this curve here is AGN plus GRB, but this is the AGN, and it just.
And GRBs are flat in this picture, right?
GRBs are flat.
Yeah,
that's
so
correct.
Any of the rises from AGN.
So that's why. So how can I then extrapolate from the measurements that IceCube had to this understanding of what I have to assume a model. I cannot.
Yeah.
Because there's no. Basically. Okay, so my question is there any AGN contribution to the events that IceCube had?
The answer to your question is, if there is, there has to be tooth fairies hiding in the production of pions in AGNs. So they can measure the photon emission from AGNs. And that gives you a very good measurement of the pion production for pi zeros. So there has to be something that's affecting the ratio of pi zero production to pi plus minus production in order to explain the lack of neutrinos.
So if you go back to this, so just to understand exactly, so if you go now or go forward to this other plot, I cannot think of, so the measurement of events at these sort of relatively low energies,
these guys.
It's not like a sideband measurement for the prediction at high energies coming from AGNs, because there is no AGN contribution.
Yeah, there is no AGN contribution.
So I can only extrapolate by assuming a model of AGNs.
Yes. Yeah.
Then this data doesn't really have any implications for my extrapolation, does it? Because
Not at
up here it's
Not for
down
AGN. No,
there it's GRBs.
these events have probably are not coming from AGNs at all. Right?
Yes. So
But-
IceCube data, I mean, we haven't learned anything new about the expectation of events at high energy
We've learned
from the IceCube data.
Yeah, so the
Therefore,
IceCube
like,
data is
still-
mysterious when it comes to AGN.
Why should you assume a model?
So
based on our model,
you can
understanding-
you can measure the pi naught production. You can measure the pi naught production directly
okay.
because the only way to get photons
Yes.
to these very very high energies is to accelerate a proton, make a pi naught, and have it decay into 2 photons.
Yes.
That's
Oh,
the only
and then,
way.
of course, they measure. So, yes.
And Fermi-Lat has that measurement, and they fit that spectrum. And so that spectrum.
That you still expect.
So those are the magical fairies that you need if you want to say, well, AGNs produce neutrinos in some funny way. You need to somehow contrive that charged pions are not produced at the rate
you still have pi
that you
zeros.
have pi zeros
Yeah.
produced.
Okay,
Because
fine.
you can measure absolutely what the pi zero production rate is.
Can I ask you?
Yes.
So I see these curves, and then I ask myself, what is the theoretical error you have?
What is the theoretical error?
I mean, just to have an idea. I mean,
So-
what would you call it as a potential theoretical error?
Yeah, so the theoretical error,
So what is
It's-
the weakest part of the computation that you can see?
the weakest part of the computation is none of the models actually predict as much flux as observed in this portion of the spectrum. So there's a lot, there's the Waxman-McCall limit, right, for nearly a perfectly efficient production of charged pions. And most models that existed for GRBs, particularly, prior to the observation of this signal, had the GRB flux an order of magnitude lower. So the original prediction for the GRBs was that it was, down here, so it would be buried in the noise. And that was kind of one of the interesting things about the IceCube signal to begin with. This signal, there's as much flux as there is in this energy range. That's why they were looking in this box. They didn't expect to find anything in this box, but they did. And that's, again, even more suspicious. There's more flux than you would naively expect there to be from the models at this energy range, but there's less in this range. So, putting all of that together, the best fit to the IceCube data for this neutrino self-interaction very much suggests that we lie in the Goldilocks zone for the the dark matter self-interaction regime. That mediator that couples neutrinos to dark matter to themselves, and neutrinos to neutrinos is all the same mediator with all the same Lagrangian level coupling constants. You find that you can fit all 3 of the dark matter structure problems: the dark matter self-interaction for the dwarfs, the galaxies, and the cluster problems, the missing satellites problem, and the mass cutoffs for the missing satellites problem, all fall in the same region of parameter space that fits the data in IceCube. So that gives us our full picture of all the neutrino portal to the dark sector. You have a Lagrangian that couples dark matter to itself and neutrinos to themselves, and these two to each other through these interactions. And kind of just as icing on the top of the cake, if these absorption features continue to persist, and it's worth pointing out that this model of every model in existence is the only model that had its fit improve with increased data after this latest data release, you can actually measure the neutrino absolute mass scale, because this center of mass energy is sensitive to the mass of the mediator and the absolute mass of the neutrino scale. And with more than one absorption trough, you can break the degeneracy and get the absolute mass of the neutrino eigenstates in the C nu B. So those produce resonant features that follow bands like this, dependent on the mediator mass eigenscale, and these white bands are where we observe events in IceCube. So you want these colored bands to be in places where there are no events. And if you change the absolute neutrino mass scale, this is how those bands kind of change their distribution. For the lightest neutrino mass being relativistic, you get this broad absorption feature. But as you move the neutrino mass scale up closer to the limit on the sum of flight neutrino masses, they all start to merge together into a single band. So some things do need to be revisited. This isn't perfect. N effective is unchanged in this minimal model, but there's no hint from what we've done so far about what the transition energy between the neutrinos having no interaction with the sterile sector and decoupling with that and populating the and beginning to scatter with active states and sterile states with masses. So we don't know exactly what the total N effective is yet. It could be somewhat larger. If you move the decoupling temperature between the TeV to GeV range, you can get a delta N effective in line with the Planck results. So delta N effective is about 0.3. And a neutrino self-interaction on the MeV-scale has implications for supernova, because it's the same temperature that the core of a supernova is. So there will be resonant production there. Although the trouble is that the supernova core is a deucedly difficult problem. This has been, people have thought about this for a very long time in the context of Majorana neutrinos. And there's no consensus in the literature what actually happens when you have some self-interaction for neutrinos that's operating in a supernova core. None of the literature is self-consistent with itself. People are still arguing about this. So that needs to be more thoroughly investigated. But the conclusions that we can draw, hidden neutrino interactions do a great job of explaining what it is that's going on with that IceCube signal, because it really, if you read their papers, they make it sound like they know what's going on, but they really have no clue. The signal does not match the predictions at all. And if these hidden interactions are a byproduct of this dark sector interaction, everything forms a single self-consistent framework. You have the dark matter self-interaction, interaction with neutrinos, and neutrino self-interaction operating all together through the same mechanism, and it all fits with observations. And the best part is that IceCube is running right now, and it's going to be kicking out data for the next 10 years. So we will, with time, have a definitive answer on this subject. So, thank you very much. Yes?
Why are you using a vector interaction rather than a scalar interaction?
You can do both.
Yeah,
it's just a choice. Yeah.
So, I mean, there's what are the different implications?
So the different implications, other than a few, let's see, you could have, it's more important for the dark matter self-interaction than it is for the neutrino self-interaction. So if I can go back, kind of the parameter space that fits the dark matter self-interactions is very sensitive to whether or not it's an attractive or repulsive potential. So this is attractive, this is repulsive. So with a scalar interaction, you really only have one choice. It has to be attractive, but with vector, you can have attractive or repulsives. So this curve is nice and smooth and easier to plot and more pleasing to the eye, so we chose a vector. Yes?
But if you have a vector and you have a mass, then you know the duplication variant, presumably there is a Higgs mechanism.
There is.
So where's the scalar?
So that scalar is.
And there is also another you have interactions there.
Yeah,
change everything very dramatically.
So that was what I was trying to explain earlier. That extra scalar can be the scalar field that generates neutrino mass. So that scalar can be the seesaw scalar that drives apart the Dirac neutrino mass eigenstates away from the central.
I mean, this seesaw is clearly not a grand unification seesaw. Because
no, it's not a Gauss seesaw, but it is an axion-like seesaw. So the operator that connects the SU2 and the active sector and the U1 sterile sector, that becomes an order 5 operator.
You mean the
Yeah.
I have to work on it.
Yeah.
But
Yes.
It's a scalar.
Yeah.
It's not a scalar.
Okay. Okay. Thank you.
Carry twice now, then twice the left number.
Okay.
So now from there. But I mean, okay. So the question is that once you make a more sophisticated model, particularly the model will be actually different predictions. Right?
Yes.
Who would expect that there's a natural skill associated with that, which is not very far away from tens of MEVs, right?
Yes.
That might change basically the resolution of the final temperature corrections.
Yes, so that's actually a very, that's what we're working on right now. Yeah. That's the short answer. Yeah.
Yeah.
All right. Any other questions? Okay.
I'm thinking, when everything works, I'm always typically...
Oh, I know, it's so scary. Yeah.
Is there anything that it doesn't work anymore?
So, is there anything that doesn't work particularly well in this model? Supernova. it will be very difficult to get a calculation that reproduces the 1987A temperature distribution of emergent neutrinos. Because you can just imagine you have this 10 MeV scalar, so the characteristic temperature of the neutrinos that are emerging that have this interaction will be, half of that, 5 MeV. But 1987A had an average temperature around 10 to 15 MeV. So hot neutrinos were emerging from this core. So if this hidden sector is there, it's going to be hard to explain how hot those neutrinos that we observed really were as compared to what we would predict here, kind of just from a back of the envelope estimate.
How about the direct detection? Through this portal, right? I mean, you can happen to electrons of the atom, so maybe there is some cross section for direct detection, right?
Unfortunately, not for the. There is a cross section for the relic sterile neutrinos, but you can compute it, and it's just as hard as calculating, as detecting the relic active neutrino abundance, because the sterile neutrino has to oscillate back into an active state in order to undergo that interaction. So a sterile neutrino left over from the Big Bang has to oscillate back into a weak interaction.
I'm talking about dark matter.
So dark matter.
Yeah. So dark matter. So direct detection of dark matter.
So there could be fermion loops, but it has to go through a weak interaction loop. So it's going to be extra.
I mean, you exchange this 10 MeV, right? And that couples to the neutrino. So through a loop, you can actually couple to some electron.
You absolutely can, but again, a weak interaction loop is very far down in strength.
So what is roughly the?
You have to be careful because it doesn't couple. That's what it doesn't couple directly to the standard model.
Yeah.
It couples to the neutrinos that are mixed to the standard model neutrinos.
But there are some parameters that this model works, right? So there is some cross section that.
You could have NSI kind of like things, but the much better way to go about this, because the neutrino, you have to have the neutrino loop. He's right. There's virtually no cross-section to go through that neutrino loop, because not only do you have to make a weak interaction loop, you have to oscillate inside that loop. And so you have to,
So it is negligible.
It's absolutely negligible. But the dark matter still could have some coupling to quarks.
But that is one of the people.
Yeah.
Sorry,
Yeah.
one last question for me. So assume that IceCube come back and say, well, actually, we don't have these gaps.
So that was why.
What would happen for the scenario of something around in dark matter? Would you still believe it?
Right. So.
I mean, assuming that you don't explain that. But
so let's say the low energy gap goes away. So that's this. We made this purple line specifically for that scenario. So there is some wiggle room, right? You can shift all of the absorption features to slightly higher energies by increasing the mediator mass. And then you explain the absence of AGN neutrinos only.
So you're just saying that I changed the mass of phi, and that would be still okay from the interacting mathematics?
Yes.
Yeah.
So,
yes.
Follow on that. What's the how much wiggle room do we have for the mediator mass from the interaction dark matter point of view?
There's quite a lot, actually. There's a range of a few decades in mediator mass, depending on the strength of the interaction and the dark matter mass itself.
Right. I just thought you said that 10 MeV was particularly good.
10 MeV is particularly good because it lands in a regime that, let me see, that Haibo Yu really likes, who's one of the authors on this paper. So, he likes GeV-ish dark matter masses, and alpha, that's 10 to the minus 2-ish, so Lagrangian level couplings, much less than 1.
In that respect, I mean, you have two parameter space, right? Chi and phi. So in principle, there is no particular. I mean, and once you normalize to TEV and to MeV, except these are different powers. One is to the 1/4 power, and the other to the first power. But I mean, there is still room for that, right? So
yes.
There's going to be a total 10 MeV.
I know there's no reason to absolutely insist on 10 MeV.
So there might be other,
right, but
other islands where it's still okay.
Oh yeah.
So it's not.
But the suspicious thing about the IceCube signal is the IceCube signal is breaking the breadth of the parameter space that you can have for just dark matter interactions alone. Right. That IceCube signal tells you what that mediator mass times the absolute mass eigenstate of the neutrino is, if that's the mechanism which is producing this absorption feature. So like it's very enticing, and I've got my fingers crossed that those absorption features persist, because you can always make a new model to explain emission, but absorption is very much harder to sweep under the rug. So if you just have holes in your signal, like we seem to be observing now, that's very suspicious. All right, thank you very much.